Welcome to the online video lecture series for Intermediate Algebra at Wayland Baptist University. This video is for Section 2-1, Introduction to Functions. This is the first video for Chapter 2 in which we begin a closer look at a very important mathematical object known as the function. At the very beginning of this chapter, we'll begin by defining what we mean by a function and how it is different, or it is a special version of an equation. We've talked about equations already in previous videos for this course, and we'll also show how it's different than just an expression. So it's a very important concept that we use throughout mathematics. And after we take a look at defining what a function actually is, we'll of course discuss important aspects like what is the domain and the range of a function, more terminology. We'll also graph functions, and then we'll eventually look at special types of functions. We'll begin with the simplest of all functions in Chapter 2. We'll talk about linear functions. Okay, so let's begin Section 2-1 by first talking about what in the world do we mean by a function. Now here are some of the essential concepts that we will be covering in this section. We're going to first of all talk about the domain and range of a relation. Then we'll determine whether or not a relation is a function. Then we will introduce function notation and learn how to evaluate functions using that notation. Consider the following list of the top 5 U.S. last names. We have Smith, Johnson, Williams, Brown, and Jones. And in the second column we have here the percentage of occurrences of that last name among U.S. citizens. So this list indicates what I might call a correspondence between the top 5 U.S. last names and the percentage of Americans that share them. Now what we can do is we can write this table as a set, okay, and we will write it as a set of ordered pairs, right? And you'll remember ordered pairs are the notation that we use whenever we're, say, plotting points on a Cartesian or rectangular coordinate system, where the first part of the pair is the x value and the second part is the y value. Well, now we're doing ordered pairs where the first value comes from this first column, the second value comes from the second column, and the fact that they're a pair means that those two values correspond to each other. Now in mathematics, we're going to refer to any set of ordered pairs like this as a relation. It sets up a correspondence between one set of objects and another set of objects. That's called a relation. And the first set, that is the set in the first column that represents the first component in each of the ordered pairs, is called the domain of the relation, and the second is called the range. So the range are the firsts in every ordered pair, and that's the domain is the first in every ordered pair, and the range is the second in every ordered pair. So if we're asked to find the domain and range of a particular relation, such as this one right here, then what we need to do is determine what are the sets that are the firsts and what are the sets that are the seconds. So the domain, which I might denote as D for domain, is going to be the set of objects given by these first elements. So let's write that down. Smith, Johnson, Williams, Brown, and Jones. Okay? Now what about the range? The range, which I will denote with R, is going to be the set of all numbers that correspond with the domain. So in this case it would be 1.006%, 0.810%, 0.699%, and 0.621%. Now I'm not going to list this one twice, even though I see it 2 times here, because this is a set, and a set only needs to list what's in the set. It doesn't matter whether it's in the set once or twice. If it's in the set, it's in the set. If it's not, it's not. So we only list elements of a set one time. So our range are these 4 values here, and our domain was Smith, Johnson, Williams, Brown, and Jones. What about for this second problem? What is the domain of that set? Alright, so the domain is what we will get by taking the first elements out of each of those ordered pairs. I'll use D for domain, and I'm just going to use roster notation, meaning list out the elements. I get 5, 10, 15, 20, and 25. Again, those are coming from here, 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 and here. What about the range? Alright, it's going to be 12.8, 16.2, 18.9, 20.7, and 21.8. Okay, so those come from here, 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 and here. So you may have the same number of elements in the domain and range. You may have different numbers of elements in the domain and range. One of the common ways to illustrate a relation is to just go back to the table notation we used earlier when we were talking about that earlier correspondence. Now, in that previous example, I had the list of ordered pairs, and you can flip back in your notes if you need to, but what I've got was I had as my domain 5, 10, 15, 20, and 25, and as my range I had 12.8, I had 16.2, 18.9, 20.7, and 21.8. And by putting them in pairs, what I meant to say was that 5 corresponds to 12.8, 10 corresponds to 16.2, 15 corresponds to 18.9, 20 corresponds to 20.7, and 25 corresponds to 21.8. Now, if we went back to the earlier example where I had the domain was Smith, Johnson, Williams, Brown, and Jones, the range was 1.006, 0.810, 0.699, and 0.621. And Smith corresponded to this value. Johnson corresponded to 0.810% of the population. Williams corresponded to this one. And what we have here is a convergence. We have Brown and Jones both correspond to the same value. Okay? Now, what happens if I switch these two? What if I said instead of having the domain was Smith, Johnson, Williams, Brown, and Jones, but the domain is actually the numbers, 1.006. Does the order matter in what I call the domain and the range? And the short answer is yes, and let me explain to you why. So here's my domain now. If I were to just switch the roles, that is, let's reverse all of the ordered pairs in my relation. I have Smith, Johnson, Williams, Brown, and Jones. And what you have here, of course, 1.006 corresponds with Smith, 0.810 corresponds with Johnson, 0.699 corresponds with Williams, 0.621 corresponds with both of these values. Okay? Now, there is a fundamental difference between these two and this one. Okay? And it's a fundamental difference that we consider very important in mathematics. If we were to think of a relation in terms of input and output, that is, I have some sort of relationship where I put in an input and I get an output, then in every case in these two, every time I put in one thing, I get exactly one thing out of it. However, in this one, because of this right here, where you have two different directions, then this one input gave you two different outputs. So what we're going to do from this point forward is we're going to define a function to be what we have here on the left. It's a relation from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. Okay, so you can have, for every input, you're going to have exactly one output. So, for example, a function might be something that has as its domain 1, 2, 3, 4, and as its range 5, 6, 7, 8. It's perfectly okay for two different inputs to go to the same output, but as long as every input has exactly one output, it's a function. But something that has, for example, 1, 2, 3, 4 as its domain, 5, 6, 7, 8 as its range, and if ever one input corresponds to two different outputs, means it is not a function. Now let us look at these two examples and determine whether or not the relation given is a function. Remember, a relation is simply a list of ordered pairs, which is what we have in both of these cases. So the question of whether it's a function is, are there any inputs, that is, any values in the first that have more than one output? And the answer is yes. Look at this. 5 has an output of 6 and 5 has an output of 7, which means not a function. You can't have the same input for different outputs. Okay? What about in this one? What about 1, 2, 3, 4, 6, 5, and 7, 5? Well, even though I see a 5 here and a 5 here, it doesn't violate the condition of being a function because you have 1, 3, 6, and 7. 4 different inputs, each giving one output. Means that that is a function. Okay? Now, one of the visual aids that I use when I think about a function is to think of it in terms of this black box or this machine or contraption where you throw things into it, it cranks away, something goes along inside and does something, chunk, 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 cranks on that number, and eventually something comes out. When something comes out, that new result is the output. So a function is something that takes an input and creates an output. Now, most of the time in a mathematics class, we are actually not going to be working with lists of ordered pairs or even tables of numbers. What we are going to do is we're going to have formulas for functions. So we're going to have a formula that we plug numbers into, we evaluate, and get a number out of. That result will be the output. So this box becomes a function that transforms input numbers into output numbers. That's the concept of a function. Now here's the notation that we're going to use from this point forward to talk about functions. We're going to let, say, for example, our variable x, it doesn't have to be x, it can be any variable, but if it's some variable that we're going to call the input, we're going to use this notation right here, f parentheses x to be the output. Okay? Now this, in earlier classes, we would have thought of as f times x, but it's actually not that in the context of a function. Whenever you see on the left hand side of an equal sign simply a name of a variable, parentheses another variable, that represents a function name and its input, and it's not read f times x, it's not even treated as a multiplication, it is read as f of x. So f of x in this case is equal to this formula. What this means is that for each input we can find the value of the function by plugging x, or whatever number we want to plug in for x, into the formula on the right hand side. So f of 10 doesn't mean multiply f times 10. It means this is a function whose name is f. Like the box on the previous slide or the previous page was a contraption that took inputs and outputs. F is the name of the contraction. 10 is the number I'm throwing into that box. And then how do I figure out what to get out of it? Well, I put 10 into the formula. So I have negative 0.016 times 10 squared plus 0.93 times 10 plus 8.5. So to figure out what the number is actually equal to, that is, what's the output when I plug in a 10, I take the 10 and plug it into the formula for the function. Then I would do some evaluation, of course, remembering that PEMDAS always rules in terms of the order that I do my operations. So I'd get negative 0.016 times 100 plus 0.93 times 10 plus 8.5. That gives me negative 1.6 plus 9.3 plus 8.5. And a quick punch of the calculator gives me 16.2. So 10 is the input, and 16.2 is the output. Again, let me emphasize over and over again, the notation f of x does not mean f times x. Now let us consider a few examples. Let's evaluate for the following functions f of x let's evaluate the following functions. In this first example, we're asked to find f of 6 whenever we know that f of x is in fact equal to 4x plus 5. So f of 6 is equal to, that means take the 6, and everywhere there's an x, we're going to put that 6. So we have 4 times 6 plus 5, which I'll work out, and that's 24 plus 5, which gives me 29. So what that says is that f of 6 is 29. If 6 is the input, then 29 is the output. We'll do the same thing for example B. Now we've changed the name of the function, but it still works the same way. G of negative 5. If this is my formula for G, it's going to be 3 times negative 5 squared minus 10. Alright, 3 and negative 5 squared is a negative 5 times a negative 5, which gives me a positive 25. 3 times positive 25 is 75. 75 minus 10 is 65. So altogether, but G of negative 5 is 65. Alright, now h of negative 4. Again, I've changed something else here. Instead of talking about f or x, I've got the name of the function is h, and it depends on the variable r. So r is my input, and h of r is my output. But that doesn't change the procedure. If I want to find h of negative 4, and I have h of r in terms of r, that means I'm going to plug in r in for everything. So negative 4 squared minus 7 times negative 4 plus 2. This gives me 16. Minus a minus makes plus 28 plus 2. Add those all up and I get 46. So h of negative 4 is 46. Now let's consider this one last example. Notice how in the first 3 examples I plugged in numbers into a function to get the output, but there's actually nothing in this procedure that requires that a number be plugged in, because all I'm doing is replacing the variable in the formula with whatever the input is. What if the input were, for example, a mathematical expression? Does that change anything? And the answer is, well, no. All I'm going to do is I'm going to put this, right? If there's an x here, I'm going to plug in that value of x right there. So what this looks like is that f of a plus h is whatever this formula tells me, except replace all the x's with a plus h. Again, notice I'm not multiplying a formula times a plus h. This actually means plug a plus h in for x. Okay? And with just one step of simplifying, that gives me 6a just by multiplying out plus 6h plus 9. So f of a plus h, the output is 6a plus 6h plus 9. And that's how we use function notation. So having talked about domains and ranges and what a function is, that's the end of section 2-1.